Okay, so welcome to our first video on differentiation. There'll be quite a lot more videos on differentiation than there was on limits and continuity because differentiation is weighted a lot more on the AP exam and there's a lot more topics to cover. So yeah, we'll have a lot more videos. And the first thing that I wanted to talk about with differentiation was related rates. And now related rates is really tricky because there's all sorts of different things that they can throw at you, but they all of the problems share like similar strategies, and so those strategies are what I'd like to share today. So okay, related rates. Before we get started on the problems, I just wanted to go over a procedure or sort of a guideline procedure thing to use when you're solving these types of problems. So the first thing you want to do is you want to write down what they want and what you have, and write these in mathematical notation. So this is something like, maybe you say dA dt is equal to 5 or something, and include units, so maybe it would be feet per second or something, I don't know. But just write it out in this math form like this, because this will help you when you're going to solve the problem and use it. And also pay attention to sign. So if they're telling you that a quantity decreases, right, then your rate is probably going to be negative, right? Decreasing usually means negative. Negative rate. And then likewise, right, if it's increasing, then that's usually a positive rate. So make sure that you have the right sign. A simple sign change can totally screw up your answer if you get this wrong. So yeah, pay attention to your sign. Okay, next step, you want to draw. Draw. This is very important. If you don't draw, your mind won't work properly to solve the problem. And we will go over a lot of different types of drawings. Some pictures, some problems may require more drawing than others. Some problems may not even require you to draw at all, but you will, like, 90% of the time need to draw. So yeah, make sure you do that. Okay, now the third step is going to be relate, so what you have with what you want. So this relation, it might be just one equation, like maybe if you have a volume and you want a rate, if you want a radius, right, then maybe right, it's a very simple, like, just one equation and then differentiate. But sometimes it can be more than that. Sometimes it can be two equations, where you have to sort of find an intermediate quantity and then plug into another equation. And we'll go over those types of problems too. So yeah, you relate it in some way. Here, so some of the major types of relations can include, this isn't a full list, but these are one of the common ones. So Pythagorean theorem, right? So usually they'll give you some sort of triangle, and then a, b, c, right? A squared plus b squared is c squared. And then geometric, so these are like some geometric formulas, like the formula for a sphere, the volume of a sphere is 4/3 pi r cubed, and so on and so on. So these equations might be used. They'll often give you these equations in the problem. They only require you to memorize like the basic ones, like area is pi r squared for a circle or something like that. Distance formula, this is a little rare, but it still can happen, right? So the formula to find the distance between 2 points. or similar triangles. So these are used mostly like in cones, or like basically anything that involves triangles is fair game for similar triangles usually. Right, so you might see it like this. This might be the cross section of a cone. So that's a tricky application that you might not see right away, but so keep that in mind. So relate what you have with what you want. With, you know, some of these you probably involve some of these types of relations. And then finally you're going to differentiate. So a few things to remember when you're differentiating. So first, don't plug in before differentiating. And the reason is, like, that value is not constant, right? So if you have like x squared plus y squared is 10 maybe, and you're trying to figure out, I don't know, dy dt, right? You cannot just plug in a value. Maybe they give you maybe they ask you to find dy dt when y is 1, and you can't just plug in 1 right here to start and say, oh, I have no more y now, where did it go? Because this is just one moment in time, and you can't use one moment in time to generalize to all moments of time that this function is trying to describe. So yeah, basically don't plug in before you differentiate, unless of course it's a constant value, in which case it's okay to plug in before differentiating. Okay, now the fifth step is just pretty obvious: plug in and solve. So plug in what you know. Maybe you've got two equations and you're plugging in quantity, but either way, you've got to plug it and solve at the end. And you may need like sort of intermediate quantities. So these are quantities that maybe it's not directly related to your equations, but they will help you find the rate that you're looking for. Okay, so that's the basic process for related rates. Now let's get started and apply this process in a few problems. Okay, so here's our first problem. So we don't really need the main question. I just put that there to give you some context that we're measuring heights of trees. We really need to read this part. So the height of a tree in meters can be modeled by the function g. Okay, so this function is important. Okay, x is diameter in meters. Always look at units. Units are super important. 50 meters tall. Okay, so diameter of the base. According to this model, what is the rate of change of the height with respect to time in meters per year? Okay, so it's a lot of information to digest, right? But let's write this out as per step 1 in math notation. So what are we trying to find out? The rate of change of height. So maybe I'll call height h. So dh, trying to find dh dt in meters per year at the time when the tree is 50 meters tall. Okay, so what determines height? Well, g of x determines height, right? So I'm going to put g equals 50. So this notation means evaluate this derivative at this point. So that's what we want, right? Okay, what do we have now? So we know that our instant that we're looking for is when the tree is 50 meters tall. Okay. Diameter of the base is increasing at a rate of that. So increasing, right? That tells me, okay, it's a positive rate. And the diameter of the base. What is the diameter of the base? Well, it's actually x, right? So dx dt. And then that's going to be positive 0.03 meters per year. Okay. And I think that is all that they really give us, other than, of course, the function, which we should write down, 100x over 1 plus x. Okay, so first thing, when you want to, like, okay, this should be a g first, sorry. I called this h because it was height, but now I realize that, okay, g is the height. So this is really a dg dt. So first, when you're looking for this like quantity, right, just go ahead and differentiate the equation that that it's involved in. So like this case, we're looking for dg dt. So I'm going to differentiate this first. And maybe if there's some like stuff we need to figure out, we can figure it out. But we'll know what to figure out if we differentiate. So let's just go ahead and do that. And now the important thing to notice, right, is we wrote dx dt here, right? So this implies that x is a function of t. So since x is a function, right, if you want, you can write this as g of x of t. Now, in order to differentiate this, right, with respect to t, you need the chain rule, right? So I'm going to write this as dg dt, and then you have to find the derivative with respect to x, dg dx, right? So this is the equivalent of f prime g of your chain rule. And then you've got to multiply by the inner function, the derivative of the inner function, of course, which is going to be dx dt. So if you don't understand this notation, you can think of this dx dt as basically the when we differentiate anything implicitly, we have to tack on this dx or dy dt, and so that's that right there. And then dg dx is just like this function with respect to x. So okay, let's differentiate. So we're going to use quotient rule, right? So that's our quotient rule right there. So 100, and then g is 1 plus x minus f, that's going to be 100x. G prime is 1 plus x over 1 plus x squared. Okay. Now, multiplied by, do not forget, dx dt. And what is dx dt? Well, we already know that. It is 0.003. So I'm going to write that here in place of dx dt. Okay, great. So that equals this rate. So what do we need? We need x. Great. So how are we going to get x? Well, maybe just look at where x shows up. But what is related to x? Oh, okay. Well, g is related to x, right? And so, okay, so we're trying to, if we were using this to solve, right, we want to find x, and in order to find x, we would need g. So do we have g? Yes, we do. At the point where we want, g is 50. So let's go ahead and plug that in. 50 is 100x over 1 plus x. Now this equation looks very intimidating just because it's a rational function, but it's actually not all that bad once you get into it. So we're just using some good old algebra here, and then we get x equals 1. Great, so x is 1. So now we just plug in x is 1 here, and then we will get our dg dt at that point. So dg dt at g is 50. Alright, so 100, and then 1 plus 1 is 2, minus 100, and then we leave that 1 out, over 1 plus 1 is 2, squared is 4. Okay, and let's not forget to multiply. I'm going to write this as 3/100ths, just so it gets easier to simplify. Okay, so that's 200. 200 minus 100 is 100. Cancel those out, and you get 3/4 meters per year. Always include units. So the units in this case are going to be meters per year, because first of all, that's the units that they gave us. Our next related rates problem is an ice sculpture. Okay, so the volume is decreasing at a constant rate of 2 pi cubic meters per hour. What rate in square meters per hour surface area of the sphere decreasing at the moment when the radius is 5 meters? So the fact that the question uses the word decreasing to describe the rate of change of the surface area should tell you that your final answer, we'll call S the surface area. So ds dt should be negative, right? because that word decreasing there tells us that it is. At the moment, okay, so we're trying to figure out ds dt when the radius r is 5 meters. And they give us two equations here, which we'll probably need to use. We also know the volume, how the volume is changing. It's decreasing at a constant rate of 2 pi cubic meters per hour. Okay, so I think that's the information that they have given us in the problem. So, okay, surface area. Which equation involves surface area? That one does. Okay, so let's write that one down. 4 pi r squared, and let's go ahead and differentiate this. So 4 pi, and then 2r, and remember r is a function of t, so you're going to have to multiply by its derivative with respect to t. Okay, so what do we need to find the surface area at this r is 5 when the time is r equals 5? So we have r already, right? It's 5 at that moment, but we don't have dr dt. So, okay, we need to find this dr dt here. Now we have dv dt, and in general, for most College Board problems, you're going to need to use pretty much all of the information that they give you, one point or another. So we probably have to use this. And I also see an equation for volume. So okay, let's write that down. 4/3 pi r cubed, and let's differentiate this. So dv dt 4/3 pi, because that's just a constant, and then 3r squared, and then again we're going to multiply by dr dt, because r is a function of t. Okay, so I know r, once again, is 5. I know dv dt is minus 2 pi, as given right here. Right, this is why it's super important to write in terms of math notation, so that it's easy for you to recognize when you have certain pieces of information. And then dr dt we don't have. Okay, great. So it looks like we can solve for dr dt because that is the only unknown. So let's do that. So minus 2 pi, 4/3 pi, and then this is going to be 3 times 25, so I'm going to write that at 75, dr dt. Okay, and now this is going to be quite annoying to simplify, but so 2 and then a 4 from up here, all over, and then a pi. Oh, let's cancel out the pi's because we have pi's on both sides, so I'm just going to erase those. So that's like dividing by pi. So we have 2 times 4 over 3 divided by 75 dr dt. I think I did my... Oh no, we have to flip these. Right, so we're really multiplying by 3/4 here, and then we're dividing by 1/75. Just doing this all in one step. Okay, and it's negative, good sign, because the radius is decreasing, because the volume is decreasing. So, right, if this is just some sort of circle, right, if the volume is decreasing, then you would expect it to shrink. So that is a good sign that dr dt is negative. Okay, so let's see, minus 6. Oh, let's do some canceling here. 75 is divided by 3, so it's going to be 25, it's 1. So it's going to be minus 2 over 4 times 25, or minus 1 over 50. And that's dr dt at that point where r is 5. Okay, great. We have dr dt, and that was the only thing we were missing. So now let's just fill that in. So dr dt is minus 1/50th. And now all we have to do is just evaluate. So we've got 4 pi, and then the 2, and the r is 5, and dr dt is minus 1/50th. And now we've just got to simplify this mess of an expression. So I'm going to just rewrite this as one big fraction so that we can simplify a little easier. So divide by 10 is going to be 5. And you get minus 4 pi over 5. And let's look at our units. This should be square meters per hour. So square meters per hour. Now we didn't need the units on this question, but on an FRQ they'll usually give you some points for the units. So make sure you do include them. Not just for related rates, but for any FRQ. Okay, so minus 4 pi over 5. Now the answer here is positive because it is asking at what rate is the surface area decreasing. So it's decreasing by 4 pi over 5 square meters per hour. You can't say that it's decreasing by negative 4 pi over 5 square meters per hour because A, that's just confusing, and B, that kind of means you're increasing. So yeah, that's why the answer is positive over here. Okay, so here's our third related rates problem. It looks intimidating because there's a big giant cone staring at us, but it's not that bad, I assure you. So, okay, inside of a funnel of height 10 inches. So let's draw that right away. This is 10 inches. Okay. It has circular cross sections as shown in the figure above. At height h, the radius of the funnel is given by that, where, okay, h is, that makes sense, right? Now this is 0 and this is 10, and h shouldn't really exceed or go outside that range. The units of r and h are inches. Okay, so they gave us this nice drawing here, so we can kind of clearly see that this is the cross section they're talking about. Okay, so the funnel contains liquid that is draining. Okay, draining. Right, so this is telling me, negative quantity, something is decreasing. Okay, so at the instant when the height of the liquid is h equals 3, so they give you h equals 3, the radius of the surface is decreasing. Okay, decreasing. Alright, so I'm going to call, luckily they already have r as the radius, so dr dt when h is 3 is 1/5 inch per second. Okay, at this instant, what is the rate of change of the height with respect to time? Okay, so they're really asking for dh dt as h is height. Okay, so what equation contains h? That's right, this equation does. So let's differentiate it. I'm just going to differentiate that without writing it down. So dr dt is going to be 1/20th, and then 2h, and then remember h is a function of t, right? Because height is decreasing with time, it is dependent on time, so we also have to multiply by dh dt. Okay, so now we have that dr dt at h equals 3 is 1/5, so I'm going to write that there, and then we know that the height is also 3. So, okay, that's pretty easy. We don't need to solve anything. It's just all there for us. Just got to solve for dht now. So, yeah, the rest of this is just algebra. So, 20 over 5 is 6 dht. That becomes a 4. And then our final answer is going to be 4 over 6. Simplify that to 2 over 3. What is our units? The rate of change is the height with respect to time. Now, what is height measured in? It's measured in inches. So this should be inches per what unit of time? Per second. So inches per second. And we must have dropped a negative somewhere. Yeah, we dropped a negative right here. So, yeah. See, even I mix up my signs. So you have to be really, really careful not to mix up your signs, because I would have gotten the answer wrong if I just circled this right here. But this is the wrong answer. And the thing that made me stop is, why is the height increasing when this funnel is draining, right? You always have to be doing those sort of does my answer make sense sort of checks to make sure that you're not screwing up. So that sort of check in my head prevented me from getting this wrong. So okay, minus 1/5, so we're just going to propagate this error throughout the entire solving. And then, okay, so our final answer should be minus 2/3 inches per second. Okay, so our next problem is as a multiple choice. This is from the 2012 practice exam. So let's take a look. Okay, so a person whose height is 6 feet. So I'm gonna label this man 6 feet. 6 feet. Make this a little more clear. Is walking away from the base of a street light. Okay, so he's walking this way along a straight path at a rate of 4 feet per second. If the height of the street light is 15 feet, what is the rate at which the person's shadow is lengthening? Okay, so two things. A, right, this whatever answer we get should be positive. Now, all of the multiple choice answers are positive, so that doesn't really help us eliminate anything. But still a good thing to keep in mind. Okay, so how does this person's shadow, how is this person's shadow created anyway? Like, how would we figure out the length of the shadow, right? Well, how shadows work is, right, from the light source, they sort of extend like this. And so this length, whatever this length is, after you extend down this way, is going to be the length of the shadow. So let's make this drawing a little clearer. And this is the street light, right? So it's 15 feet. And we know we've also got this person, 6 feet. And we've also got some sort of shadow. And we know that in order to find shadow, we have to extend. So, oh, this is interesting, right? It looks like a triangle. Why not complete the side of a triangle, right? So this is starting to look like similar triangles, right? We've got two triangles sort of nested inside each other. Okay, so he's walking away at 4 feet per second. Okay, so what does that correspond to in our drawing? Now, pro tip. Give things names. If you give things names, you can start to say things about them mathematically. So let's call this A. Okay, so if this is A, and this is the shadow, this is what we really want. So what we really want is dA dt, right? Because dA dt will give us the shadow length. Okay, so I'll highlight this in red to make this clear. And then, okay, we'll call this B, right? So if this guy is walking away, then B will increase. B will increase at a rate of 4 feet per second. 4 feet per second. So now what? We want dA dt. We have dB dt. So we've got to relate B to A somehow. So how do we do that? Well, let's see. Similar triangles tells us that the ratio between corresponding sides will be the same. So 15 over B plus A equals 6 over A, right? So this divided by this is the same thing as this divided by that, right? And we know that because it's a similar triangle. So now we can sort of cross multiply, divide by 3, and then I'm going to expand as well. Oh, that should be a 2. Okay, and now we're going to subtract 2A. Okay, cool. So we've got a relationship between A and B. So now we just differentiate. So 3 dA dt equals 2 dB dt. And from that point, we're pretty much done, right? So dB dt is 4 feet per second. So you know this is 4. And so we can just solve for dA dt right now. So it's 3 dA dt equals 2 times 4, which is 8. So then dA dt is going to be 8 over 3. And then what are the units going to be? So it's lengthening, so that's good. A is positive. And what are the units? Units are going to be feet per second. And 8 over 3, okay, we need to convert this to decimal, so 2 2/3, so this is really going to be 2.666, so on. So, yeah, it's going to be answer B, because you'll get, that's about 2/3. Okay, so our final problem, we can use our calculator. So let's look at this. So Mr. Brust is using a ladder. Okay, so 17-foot ladder is leaning against the house. So this is the ladder right here, and so the ladder is 17 feet, and it's always going to be 17 feet long. Okay, 17-foot ladder is leaning against the house when Mr. Kelly decides to pull the base of the ladder away from the house. Okay, so what does that mean? So maybe this is Mr. Kelly. Okay, and he's pulling this way. So what's going to happen? Well, this length, again, give things names. So maybe we'll call this length A, and this length is increasing. So dA dt is increasing at a rate of 3 feet per second. Okay, great. How fast is the top of the ladder moving down when it's 8 feet above the ground? Okay, so again, this looks very close to a triangle. So maybe I'll just complete it, right? Because triangles are fun, and we can do trigonometry and all sorts of theorems. So in general, as we saw in the last problem, completing triangles is usually a good idea. And I'll give this side a name. Oh, B. Okay, so it's 8 feet above the ground. So that means B was 8. And so I use this little parentheses to indicate that this is only one moment of time. So B is only 8 at one moment of time. It is not always 8, right? Because if the ladder falls, maybe it falls like this. B is no longer 8. B is less than 8 in this scenario. So the ladder is just, falling. So B is always changing with respect to time. So that's why I put this little parentheses here to remind myself that this is not a constant value, and so I should not plug it in before I differentiate. Okay, top of the ladder. How fast is the top of the ladder moving down? Okay, so what does that mean? Well, how do I measure how far the top of the ladder is moving down, right? It's really just this side length B. So since we're looking for how B is changing, right? dB dt is what we're looking for in the end. So okay, armed with all this information, now we've got to relate. So we have a dA and we want dB. So let's relate A to B somehow. How can I do that? Well, this is a right triangle. So by the Pythagorean theorem, we have a squared plus b squared is 17 squared. So, okay, now let's differentiate, right? Because we have a b in there, so let's differentiate and see what we need to find. And once again, we are implicitly differentiating, so we have to multiply by dA and dB dt because they are both functions of t. They are both changing with respect to time, right? And the derivative constant is 0. Alright, now let's factor a 2 out of this because I want to. And also this makes things easier. Equals 0, and then we can just divide by 2. Okay, cool. So now what do we need? So dB dt is what we're looking for, right? We know what B is at that moment. It's 8. We don't know what A is, but maybe we can find out. So we have two sides. We have an 8. We have a 17. And we're looking for this side x, right? So we're going to use the Pythagorean theorem again, right? So x squared plus 8 squared is 17 squared. X is root 17 squared minus 8 squared. Okay, and you can plug this in on a calculator, and you should get 15. Okay, so x is 15. So 15, that means A is going to be 15. And again, I'm putting parentheses around there to remind myself that this is only one moment in time. Okay, so A is going to be 15. What is dA dt? Do we have that? Oh yeah, we do. Again, really important. Write your information in mathematical notation. Okay, that's going to be 3, and it looks like we pretty much just have to plug in and solve for dB dt now because that's the only unknown. So let's do that. So 15 times 3 is going to be 45 plus 8 dB dt equals 0. 8 dB dt equals minus 45, and then dB dt is minus 45 over 8, and what is the units here? Feet per second. Right, so that means that the ladder moves down at a rate of 45 over 8 feet per second. So again, our answer is going to be positive here because we're measuring the rate of decrease. So yeah, but it is a good sign that the BDT is negative, and it should be negative because B is decreasing. Okay, well, that was our final problem that we had here, and I will see you guys in the next video.